The rest of that, and this I put on its separate page by itself because translation's got a couple different things that we're looking at. I put this on the page that has the little chart that we glued the chart on the bottom. I don't have that handy, apparently. So it was the last insert that we had the other day, and I told you just to glue it on the bottom of the, or tape it on the bottom of the next page. So I've got this on the top where that chart's at. So you may want to relocate your chart and have it in the same spot where this is at because we need that chart for translation. All right, so we highlighted some of this orange. What does the orange part represent? Translated? Untranslated region. Right. That's important because this is not part of the protein that gets made. This is the untranslated region. So this, the GTP, that's what's helping to align it with the ribosome. The GTP gives it a little extra energy so that we can start the process with it. The exons are the part that is the message that eventually, sort of, that's even somewhat of a lie, becomes translated. So let's see, which one did I use? I don't want to look at this one just yet. We'll come back to that. But I want to look at AGA. So you've got your chart down there at the bottom. I thought I had an extra chart somewhere. Hang on. Not that one. I don't want that one. Well, apparently not. Okay, well, I can work with that. All right, so pencils down for just a second, just so that I can explain. Just give me a second to explain. So we did talk on Thursday about the fact that on our message, these nitrogen bases, these letters are in groups of 3. What are the groups of 3 called? Group of 3 on messenger RNA. What's a group of 3 nitrogen bases on messenger RNA called? It's the codon. So the 3 letters, the 3 nitrogen bases on messenger RNA, those are codons. So you look at one codon at a time. You look at one group of 3 letters at a time to see what it translates into. We use the codon chart in order to translate a codon to find out what it translates into. The codon chart, the first one that we're looking at, it just has letters in it. That's not a real codon chart. This is just to give us practice translating a messenger RNA. So I'll give you another codon chart that's a real codon chart that has amino acids in it. But each of the letters that are in the codon chart in the middle, those represent amino acids. Amino acids are the monomers that bond together to create the big polymer, the big polypeptide. Polypeptide is a protein. So I'm going to skip the AUG codon for just a second, and there's a reason for that. But I'm going to look at the next codon. The next codon says AGA. Do you see where I'm at? Yes? No? Shake your head. Okay. All right, so I'm going to look at the second codon. Now, don't write down anything just yet. I just want you to listen for just a second. So, on this second codon, AGA, I've used some color in order to help me come back, so in case I have issues with it later on, then that helps me figure out, well, how did I figure out that AGA represents the letter B? So AGA, on our codon chart, you'll notice it says first position, second position, third position. So first position, I used red, and I colored in this column. Second position, I used purple, and I colored in just this row. Third position, I used orange, and I colored in that column. Makes sense so far? So you basically have to kind of coordinate all 3 of those and see where they intersect. So my first letter is A. First position, letter is A. Second position is a G. Third position is an A. Where do they all come together? They all intersect at the letter B, so AGA represents the amino acid, the letter B. Does that make sense so far? Okay, so I skipped the first one for just a second, AUG. Do me a favor and run through, find out AUG, and tell me what it says. What does AUG code for? Do we know? Start or? Okay, so A, U, G, it says start/Y. So, since AUG is the very first codon on here, do you think that it's going to be the start or going to be the Y in this position? It's at the very beginning, so AUG in that position represents start. But if you see an AUG after the start, then it codes for the letter Y. Does that make sense? Okay, so hang on just a second. I'm going to have you do this in just a moment. In just a moment, I want you to use that example. Mark your chart however you need to help you understand that that's what's happening. Come back up here to your translation to your messenger RNA. We said this is an untranslated region. I use that because I know that's what it means, so spell it out if you don't. You just told me that AUG represents start, and I agree because it's at the beginning. We figured out that AGA represents B. So I want you to set this up for yourself, and then I want you to translate the rest of the translated region on your messenger RNA. Make sense? Know what to do? All right, have at it. So, diagram your chart. Okay, so for our messenger RNA, the GTP cap was put on during RNA processing. Prior to that, there would be a section of DNA that was the promoter section that would tell RNA polymerase where to hook onto the DNA to start making the message. So messenger RNA starts making the message. It starts making the message. There's an untranslated region. There's introns, exons, untranslated region. And then within the DNA, there is a terminator sequence. And that terminator sequence tells the RNA polymerase to stop. But all of the promoter, the Tata box, the intron, exon, all of that stuff, that's DNA. This is what RNA polymerase spits out, and then it gets processed. So we cut out the exons. We added the 2 caps. We still have the untranslated region. We have all of the exons ligase together. We have the poly A tail. So GTP, the untranslated region, helps to orient and helps to bind it to the ribosome. So this region right here tells the messenger RNA how to attach to the ribosome. The Tata box, the promoter region, that was code on DNA that tells RNA polymerase where it attaches. This tells the messenger RNA strand where to attach. So it's 2 different things. It's not the same thing. The start codon tells the ribosome this is where you start using the codons to find out which amino acids that you need. So this is not part of the message. This is not part of the protein. This is not part of the protein. It's just, this is where we get started. AGA, we said coded for the letter B. What's our next codon? What's the next codon? GUG is the next codon. What does it code for? It codes for I. So that codon codes for the amino acid I. What's the next codon? What's the next codon? UUA is the next codon. What does it code for? It codes for the amino acid O. How are we doing so far? Uh-oh, you had a mutation. So either that was an exon that was in there, or maybe you had an untranslated region that shifted it. I'm going to assume that it was an exon. You said CAC. because we've got a CAC right there. We've got a CAC right here. I'm going to guess that you had an exon that didn't get completely trimmed out. Okay, but that's fine. We're okay. We're going to talk about mutations later on anyway, but your protein's been mutated. Okay, for this one, our next code on GAC, what is it code for? GAC? Double check, because GAC should be an M. Do you see how we get it? Okay, what's our next code on? CUU, what is it code for? What's our next code on? Good morning, happy Monday. What is CUA code for? What's our next code on? And what is it code for? Okay. Do we find the letter for CAC? No. CCC? That is untranslated regions. So the stop codon tells our ribosome, okay, this is it. This is the only thing that you code for. We're done right here. And it will detach from the ribosome because its polypeptide has been made. Each of these represent a amino acid molecule that the ribosome binds together, kind of like a chain, if you will. Untranslated region, start codon, amino acids, stop codon, untranslated region. But that's the messenger RNA, and the messenger RNA will be destroyed, if you will, because you don't need it anymore, because the protein has been made. How are we doing so far? Thumbs up, thumbs down, sideways. So you didn't have your UGA either? Okay, so somewhere in there you ended up probably gluing together maybe a exon into your intron, or an intron into your exons or something like that. So you can get another strip and we can throw it on top of that and you can fix it the way it's supposed to be. But you had a mutation, and mutations happen. The thing is that in a cell there are all of these little particles, these little molecules that go through there and they double check. And they're making sure that everything is correct. And chances are that that messenger RNA strand would never have ended up being translated because something would have figured out that that wasn't correct and would have destroyed it. But every once in a while, you know, it gets missed. Those little particles are tired just like everybody else. Whatever, sure, it's fine, go on. And so that can end up being one of the diseases that ends up being affecting a person, is now we have these proteins in there, and these proteins aren't the correct protein. Hopefully, because they're not the correct protein, they just act like a key that doesn't fit. But it might be a protein that still works, it just doesn't do what it's supposed to. And those could end up being a prion disease, and prion diseases are really bad. So, but it happens. Okay, so Biomed is the polypeptide, the protein that was formed. I mean, we used a word just so it's nice and visual. Polypeptide, poly, many. Polypeptide's another name for protein. Each letter represents an amino acid. So B is one amino acid, I is another amino acid. Okay, so now we can add the rest of this information in here. So the macromolecule protein synthesis creates the polymer protein. Polymer, large molecule. A protein is made up of monomers, mono, one, subunits. Proteins are made of amino acids. The polymer protein is made up of monomers, amino acids. There are only 20 different types of amino acids. That's it, just 20. But there are tens of thousands of different kinds of proteins. polymer is a protein. It's made of monomers, amino acids. There are only 20 types of amino acids, but there are thousands of different kinds of proteins, tens of thousands of different kinds of proteins. There are only 20 types of amino acids, but there are thousands of different kinds of proteins. So let's think about that for just a second. How can we possibly have thousands of different kinds of proteins if there's only 20 types of amino acids? How did we say that, or what did we say was the key for the differences in our DNA? Because we're all different, even though most of our DNA is the same. What was the difference in the DNA that made us each unique and different? The combinations, the order of the base pairs made each of us unique and different. Same thing for proteins. You only have 20 amino acids to choose from. Many of the amino acids code for the same, many of the combinations that we have code for the same amino acid. It's the combination. It's how these things are put together and what order they're put together that makes the different proteins. Think of it like the alphabet. 26 letters in the alphabet, right? But how many different words do we have? And how many different sentences can you make from those words? It's all just due to the combinations of those letters. It's the same situation here. We only have 20 different types of amino acids, but you have lots of different combinations. So in just a moment, you're going to grab a codon chart that looks like this. And so on this codon chart, obviously we don't have the letters, and these each represent an abbreviation for a different amino acid. You're going to use this codon chart the exact same way, but this time you're not making a word. This time you're going to put things together to make characteristics for a critter. But you're going to use it the same way. First position, second position, third position, and you're going to find out where they all come together to find the correct amino acid. On this one, AUG, MET represents your Y start codon. So it's MET if it's somewhere in the middle of the message. It's start if it's at the beginning. So if you need to make a note of that on your amino acid chart or on your codon chart, that's fine. I don't think the little activity that we have will have start and stop on it. I think it's just going to be the meat of it just to give you experience using the codon chart. So I don't think you'll have to worry about start and stop. And stop is on here. All right? So in just a moment, you're going to come pick up several pieces of paper. One of them is that codon chart. One of them is a blank sheet of paper. And then you've got two worksheets. On the white worksheet, you have 4 different critters. These critters are snorks. So choose one. You are not doing all 4. Choose one of these critters. For whichever critter that you choose, you are then, oh, maybe it does have a start codon on here. Oh, I lied, didn't I? You are then going through and using that information to translate that into the appropriate amino acids. So what does AUG stand for? What does GUA stand for? But this time you're using the amino acids, you're not using the letters. Then it will tell you for the genes that you're looking at, whichever gene that you're decoding. So if this is the amino acid sequence that you end up with, then that means your snork is hairless. Whoops. Congratulations. If on your first gene this is the sequence, then it's fluffy, etc., etc. That brings in the blank sheet of paper. You're going to draw your sketch, your whatever snork. I'm not worried about anything besides the characteristics. So what we're looking for are the characteristics that are on here. All snorks are different, so you get to decide, just like all people are different. But I could look out into a crowd and see a hairless person, right? Okay, so we're focused more on the characteristics than on anything else. So if you want to draw a stick person and then add those characteristics to it, then I'm fine. So it's basically about giving us a visual of what that critter looks like, because then we're going to mess with their DNA later on. Sure, whatever. Okay. So like I said, if you just want to put a stick person on there, I mean, these are the characteristics that we're looking for, and then specifically, you know, what those characteristics are. So eyes, small, large, circular, rectangular, that's what we're looking for. Yes. Well, yes, you're going to have a gene as to whether you're plump, skinny, pear-shaped, hourglass. So yes. I mean, it'll give you a little bit more. But like I said, if you start with a stick person and add stuff on there, that's fine with me. All right. Any other questions? Okay. So you need codon chart, both the worksheets, blank sheet of paper. Choose one